Welcome back to minerva-tutors-tv, or welcome if it's your first time, and to today's lesson, which is all about volcanoes, with our fantastic Chief Science Tutor, Jack, who many of you will know quite well already because he's done so many lessons for us already. If you built your model volcano in last week's lesson, or between last week's lesson and now, and you've got your vinegar and your baking soda and your optional red dye or paint with you, and an adult supervising, then in the second half of the lesson, once Jack's taught us all about eruptions, you can follow along with him and make your own volcano erupt. If you haven't got those things with you though, don't worry, because we'll send the instructions out after the lesson and you can do it with your adult supervising you in your own time. Just before we start, it would be fantastic if you have built a model volcano, if we could have a quick look at it. So if you have got a model volcano in front of you and you feel like turning your camera on just for a minute, I know Jack would love to see that volcano in its form now. So if you've done that, maybe just click your camera on and we'll take a little look.
Everyone, welcome back if you joined us last week. I love seeing your volcanoes and they look really, really good. Rivaled even mine, and I know I spent loads of time on mine, so you must have spent a lot of time making yours. If you haven't made one yet, don't worry, you'll have a chance after the lesson to make one and explode it as well. But for those of you who didn't join us last week, and some of you might be new, just a quick recap on the things we went through last week, and for those of you who might have forgotten. So last week, we started by talking about the Earth's structure. And we said that we live on the crust of the Earth, and that's sort of the outer layer. And then you've got the hot core and the hot mantle inside the Earth. And the mantle itself is where the magma comes up. And when it comes to the top of a volcano, it turns into lava, or it doesn't turn into, it stays the same thing, but we just call it lava, and it erupts from the volcano. We'll be looking at the eruptions today a little bit more. We also looked at the structure of a volcano. So again, for those who weren't here last week, or for those who might have forgotten, the key points, whether at the bottom we've got this magma chamber, which is where all the magma in the volcano is stored originally. It then can rise up this main vent up to the crater at the top when an eruption is happening. So that'll be the key words we'll be using today. Magma chamber at the bottom, main vent taking it up to the crater where an eruption can happen. We also looked at making, saying that we could make one of the 4 types of volcanoes, and the 4 types were a shield volcano, a composite volcano, a lava dome volcano, and a cinder cone volcano. So you've got them here, and you can see the subtle differences that we were talking about last week. So for example, the shield one is quite flat, it's not very steep compared to the composite one, and the cinder cone ones, which are a bit steeper, and the lava dome itself, which has this sort of dome-like shape, hence the name. So that's what we were looking at last week. And this week, we're going to look a little bit more at why volcanoes erupt and the types of eruptions that we can have. So volcanoes normally erupt because the magma chamber at the bottom of the volcano, it starts to fill up. And it can fill up from magma moving up through the mantle, up through the crust into the magma chamber. And once it's full, then the only place this magma has to go is up the main vent. And it will rise and it will rise until it gets to the crater of the volcano, which we would classify as an eruption. Now, there's a couple of types of eruption that we can have. The 2 types of eruption completely depend on how much gas is in this magma that is rising up and rising up. So with quite runny and quite thin magma, so maybe magma that has a similar consistency to it, to water. It's quite runny. If I move the glass side to side, you'll see that it will move quite easily. Gas isn't held very well by water. Like for example, if I get a straw and I blow into the water, you can see and you can hear there the bubbles being made, and as they're rising to the surface, they're popping. And again, we've got no bubbles in the water. I blew the bubbles in there, but they rose to the surface of the really runny water and popped. So that's exactly what's happening with runny lava. So with the runny lava type, we're getting these bubbles that are still being formed, but they're not staying in the lava. If we have a lava that's a bit thicker, and so for this example, I'm going to use something like peanut butter. So I'm just going to scrape a bit of peanut butter onto a piece of paper here. And I'm going to try and blow bubbles into that. And what you should see is as I do that, one, it's very, very difficult to do, but two, there's no bubbles coming out the top. It's not bubbling. And that's because any air I'm blowing in that's getting stuck in, it's getting stuck in the thick peanut butter. So it's happening the same with sort of thick lava. I'll try again to get a few more bubbles in there. You could hear this, a slight release as it popped there, a noise, but that's only because we put an air pocket inside that popped. But what's happening as I'm blowing into it is the air is staying inside the thick peanut butter. So that's what's happening with the lava. And that leads to these two types of explosions. So the runny lava, kind of like the water, the runny lava leads to a non-explosive eruption. And with a non-explosive eruption, it's tends to be less deadly because it's non-explosive. There's no explosions going on. What's happening is this really runny lava is running or being pushed up the vent to the crater of the volcano. When it gets to the crater, it's just pouring out. It's not creating a huge explosion and being catapulted into the air. It's just pouring out the top. So it tends to be less deadly because lava, although it can be, if it was as runny as water, for example, it could move as fast as a river, but compared to explosive reactions, it's a lot easier to get away from that than it is the effects that an explosive eruption might have. So it's quite slow moving. So normally in these types of eruptions, people aren't harmed, but property can be harmed because, again, you can evacuate your house if you live near a volcano and it's having a non-explosive eruption, but you can't pick your house up and move it. So it tends to be the worst things that happen with this type of eruption is property destruction or farm destruction, land destruction, rather than killing people and things like that. The other type with the thicker lava, with sort of the peanut butter example lava that doesn't flow as well, it's sort of very gloopy, it's trapping a lot of gas, it creates an explosive eruption. Now in an explosive eruption, because there's so much gas in the magma, the gas is building up and building up and building up. It's creating a very high pressure in the volcano as the magma is rising and rising with all of this gas. Eventually the pressure gets too much and it creates a huge explosion. It'll create an explosion noise, like a big bang as well as it's doing it, but it'll explode upwards and propel a lot of hot ash into the air. And this hot ash itself is not only made of hot gas, but also made up of small particles, of small chunks of magma, or lava as we can now call it, because it's finally gone up the vent and been forced out the top of the volcano. So it's got chunks of hot rock, hot lava, hot gas, making up this ash cloud that can sometimes be, it exploded so high, it can go up to 100 miles. The ash, so the explosion happens and hot rock, hot bits of magma get fired up to 100 miles away from the crater of the volcano. So huge distances and big explosions happening here. A lot of the magma itself, and you'll see with this one here, there doesn't, although we're very, very far away, it doesn't seem like there's a lot of lava coming out the top of it. And that's because within this explosion, most of the lava or the magma, the hot rock, is being pulverized into these tiny chunks, which are being thrown into the air. And whenever we've got these tiny chunks being exploded into the air from an explosive eruption, we call these volcanic bombs. And these pieces can travel up to 5 kilometers away. So the ash itself, the sort of smoke gases can travel further, but the huge chunks that are being exploded into the air can only travel 5 kilometers, which is still quite a distance, considering their size. So their size, they can be about 4 to 5 meters in length, which is slightly bigger than a car. So imagine if you're stood next to a volcano and it starts erupting and suddenly you get a rock, a really hot molten piece of rock the size of a car land right next to you. Absolutely terrifying. But that's not even the most dangerous part of an explosive eruption. The most dangerous part is easily the pyroclastic flow. Now, the pyroclastic flow of a volcano is when some of this hot ash, these sort of big clouds of hot ash and hot air, start bellowing down the volcano, so going down the volcano, kind of like an avalanche. And this hot ash, this pyroclastic flow, can be up to 1,000 degrees Celsius. So anything that's in its path is just being burnt to a crisp straight away. And you may think, well, it might be easy to get away from that. It's not, because it can go up to speeds of 450 miles per hour. So very, very quick. And then just to give you an idea of scale of how quickly that's moving, it's moving just a tiny bit slower, but about a similar speed to a commercial plane. So planes are used to go on holiday. The speed that they're traveling at is the speed that this ash, this pyroclastic flow, is bellowing down the mountain after this explosive eruption. So that's the most dangerous part, because anything that's in its path, people, houses, forests, are all completely burnt to a crisp and covered in this ash. So with explosive eruptions, we have these huge volcanic bombs. We've got this dangerous pyroclastic flow. It's a good thing that we don't tend to have too many volcanic eruptions per year, especially in Europe. But if I transport you back a sort of a few million years to prehistoric times and sort of the Jurassic period, where we've got lots of dinosaurs, there was a lot more volcanic activity at this point. And the reason why that was is, if we go back to last week's lesson, when we're talking about tectonic plates, the main reason as to why there was a lot more volcanic activity is at the start of the Jurassic period, or just before that, at the start of where we started having dinosaurs, the continents on Earth, so sort of North America, South America, Africa, Europe, Asia, they're all in different places. They were making up one super continent here that we call Pangaea. And we now know, obviously the world doesn't look like Pangaea anymore, because each of the plates that these continents are on, so you've got the North American plate right over there, South American plate below it, you've got the Eurasian plate here, all of them have been moving apart from each other because we've got these tectonic plates moving. And we said last week they're moving only about 2 centimeters away from each other per year, which doesn't seem a lot to us, but over millions and millions of years, it's a big movement and big changes, which is how we've got from this to what we have now. And they're still moving apart even further, especially North America and Africa. You see they were once joined here. They're still moving apart in opposite directions, but only by 2 centimeters per year. So at this time, when Pangaea started so at this dinosaur time, when Pangaea started to move apart from each other, and create the continents as we know them now, there was a lot of plate movement, and a lot of the plates moving side by side. And we said when the plates are moving side by side, riding up on each other, or pulling away from each other, it can form volcanoes and form volcanic activity. So there's a lot more eruptions then. And it's actually, most people, it's now sort of common knowledge that a giant meteor hit the Earth and made the dinosaurs go extinct. But that was certainly helped by the amount of volcanic eruptions that were going on at the time, because there was a lot more volcanic eruptions than there are now. Again, dangerous pyroclastic flow that would even kill a dinosaur. We've got these volcanic bombs, and also by producing lots of ash and big, huge ash clouds, it can sometimes block out the sun in certain areas. Now, if you're blocking out the sun in an area, it's going to mean that all the plants in that area will die, meaning that there's nothing for the herbivores to eat, which are the ones that eat the dinosaurs that eat plants. If there's nothing for them to eat, they will die out, meaning there's nothing for the carnivores to eat, meaning that the things like the T-Rexes will also die out from this. So this would, volcanic activity like this would certainly have had a big impact on the dinosaurs going extinct, and then the meteor might have just helped finish it off. That's what we think. So now we've got a lot less of these active volcanoes, and the reason for that is a lot of them are in the dormant stage. And it's because the crust, again, is moving. These tectonic plates are continuing to move. And at this point in time, so if I just go to this picture of the tectonic plates, this is sort of a 3D image of how you can see the modern day plates separated. They're still moving away from each other. But the volcanoes that were once able to erupt are now becoming either dormant or extinct. And the reason why they're becoming dormant or extinct is because their magma sources, the sources of magma to the magma chambers, are no longer aligned with the magma chamber. So as they've moved, the magma chamber has moved out of the way of the part of the mantle that was supplying it with magma. So basically it's dried up of all the magma in the volcano, so it can no longer erupt. Now we can put volcanoes into 3 categories. We can put them into an active category, which is ones that have exploded in the last 10,000 years, or have erupted in the last 10,000 years. we can put them into a dormant category, which we sort of mean is sleeping. It hasn't erupted in the last 10,000 years, but we've got a good idea, a good reason to believe that the magma chamber below is still full of magma and that it could erupt in the next 10,000 years or so. And then we could say the third category we can say is an extinct volcano, meaning that it hasn't erupted in the last 10,000 years and we don't think it will. We think that the magma chamber has become sort of de-aligned with the part of the mantle that once was sort of sending magma into that magma chamber and filling it up. We think it's now de-aligned, so that's no longer possible, and it's just basically now a tall mountain, for example. So that's a little bit more on volcanoes there. Some of the most famous volcanic eruptions, or one of the most famous, was the one that went off in Pompeii in 79 AD. So sort of Roman times. Around this time, the town of Pompeii, Pompeii itself is sort of a coastal town, or a city, as it would have been classified in the Roman times, because it was much bigger. There's much more people living there. But it's a coastal city in Italy. And it was seen at Roman times as a very, very pleasant place to go on holiday. And we'll sort of, here you go, here's an image of what it would have looked like at the time. And in the background, almost ominously looking over the city of Pompeii, you can see a volcano in the background. Now, the Romans didn't know that this was a volcano. It's called Mount Vesuvius, and it hadn't erupted in the previous 1,800 years before this eruption in 79 AD. So they just, in fact, the Romans didn't even have a word for volcano because they didn't know it was a thing that could happen. So we'll imagine their surprise when in 79 AD, this volcano, this Mount Vesuvius, suddenly went off with a loud bang and sort of created, there was an explosive eruption of Mount Vesuvius. Now, because it was an explosive eruption, instantly the people felt these volcanic bombs landing and destroying areas of the city of Pompeii. So a lot of people, instead of choosing to evacuate, chose to stay inside and thought, oh, we'll just wait for whatever this is. We'll wait for it to end and wait for it to stop. That turned out to be a big mistake because, of course, as we know now, we've got the pyroclastic flow coming in next, which is the avalanche of ash that buried the city of Pompeii in 14 feet of ash. So buildings, artifacts, people just got buried in this really, really hot 1,000-degree ash that moved through the city, killing everyone instantly because it was moving at 450 miles per hour, killing everyone instantly and covering everything in ash. Now, what this has meant, sort of thousands of years later, is Pompeii is actually a very good site for archaeologists because ash is very, very good at preserving artifacts, preserving skeletons, preserving buildings. So the city of Pompeii, when it was covered in all of this ash, thousands of years later, when we dug it up, we found it exactly as it was on the day. In fact, you can see the people here have been covered in ash and preserved in their form. But we've kind of got a good layout of what the city would look like. So that's why we've got this sort of recreated image here as well. So that's an example of one of these explosive eruptions that can be very, very dangerous. And the eruption in Pompeii, actually in 79 AD, it happened one day after a day that was meant to be a festival for the Roman god of fire. So that really put the fear into the Romans like nothing else had ever done before. They thought they'd done something or not celebrated hard enough on that day and upset the Roman god of fire. And in that case, he released this hot, fiery ash and destroyed one of what was at the time a popular tourist city because it was on the coast and it was a very important town for the Romans. So yeah, that's an example of an explosive eruption. An example of a more recent eruption that was a non-explosive one was the one in 2010 that was of the eruption of, and I'm going to butcher the name of this one, but Eyjafjallajökull is the Icelandic one there. I've sort of looked up many times how to correctly pronounce it with its Icelandic name. That's the closest I've got. So after the lesson, if you want to have a look at it and sort of Google the pronunciation, give it your best go. But I think they're making sounds that I can't make with my mouth. whenever I try. So yeah, with Ijafayakul erupted with a non-explosive eruption in 2010. This wasn't particularly dangerous, but it did have other side effects. So one of the side effects with this non-explosive eruption is it created a lot of ash. Now this ash wasn't a problem. It didn't have a pyroclastic flow that destroyed towns and cities, but it went up into the atmosphere, which blew it towards cities like London, Manchester, Glasgow, Oslo as well. Sort of this side of Europe was the air was completely full of ash. So it meant that it grounded a lot of planes. So that's an example of how we don't have a catastrophic volcanic eruption in terms of destroying things, but one that can also impact the world and people's lives without without physically destroying them, but meaning that they can't do normal things that they would want to do. So we're not going to be using magma, we're not going to be using lava in our explosion today. One, it'd be expensive to get hold of. Two, very, very dangerous. We're going to be using an explosion that some of you might recognize from a few lessons back when we were talking about our rockets and fueling a rocket. So in that experiment, we reacted vinegar with baking soda. And just to remind you of how that works, it produces a gas called carbon dioxide. And we used that previously to send our rockets basically to launch our rockets into the sky. We're not going to be using it to build up pressure this time. We're going to be using it to recreate the bubbles in our magma as we're exploding our rockets. And the reason why it produces carbon dioxide is because of something called the pH scale, which we can see along here. So on one side of the pH scale, we have colors like red, orange, and yellow. And just above that, we've got numbers like 1, 2, 3, and 4. Now this side is the acidic side of the pH scale. So everything over here, we can call an acid. So that's things like vinegar, things like lemon juice. We've got that, the one we'll be using is vinegar. On the other side, we've got the opposite to acids, the blue, the green side, which has numbers like 11, 12, 13, and 14 above it. Now, these are called alkalis, and alkalis are the opposite to acids. They're not acidic at all. But when we react an acid and an alkali together, they meet in the middle of the pH scale with a neutral solution here. And neutral solutions are things like water, and things like salt is a neutral solution as well. And that's what we're creating when we're reacting this acid and this alkali together. We're creating a neutral solution, and by doing that, it gives off the gas carbon dioxide. So I'll sort of show you what the reaction will look like inside our volcano now. So I'm just going to pour a little bit of vinegar into a glass just to show this, and I'm going to prepare a small teaspoon, of baking soda. And what we have with this is when I pour the baking soda into the vinegar, we have quite a fast reaction that's creating quite a lot, as you'll see here, quite a lot of bubbles and quite a lot of carbon dioxide. These bubbles are being released. So in this case, it probably wouldn't lead to an explosive reaction. But we saw how it almost erupted over the glass. Now with our volcano, we'll actually want it to erupt over the glass or over our bottle that's inside our volcano so that we can have our lava bellowing down the mountain. So we'll get into that in a minute, and we'll get into the exact amounts to put into our volcano to get the best results and how to do it to make sure you've got a controlled explosion. But before we do that, if you've got any questions that you might want to ask on any of the stuff we've just been through or anything to do with the volcano, the experiment itself, type them in the chat and Lawrence will have a read through those and hopefully we'll answer some of the most popular ones.
Great, thank you, Jack. Yes, as Jack said, if you've got a question about anything about volcanoes or what you've learned today, just type it into the chat and we will ask Jack a few of them. I'll start us off with some questions we've had in advance. Where can you go today to safely see lava in the world?
Good question. There's, in terms of Europe, there's quite a few volcanoes that we consider active. And you can do tours of these volcanoes where you can go down into the caves. So one of them, Sicily, it has particularly got a few, which is sort of an island in the Mediterranean. And when you're going down into the caves to try and see the lava or magma, what you're actually doing is you're finding some of these secondary vents that are coming off the main vent, and they're deep inside the volcano. But what you can actually see is pools of lava that are slightly coming to the surface. It's very unimpressive. It's not at all an explosive reaction. But you can also find in those volcanoes areas of heat source where the rock is hot to the touch. So underneath it must be either some sort of a magma chamber or part of the main vent that's producing a lot of heat.
Brilliant, thank you. I've got a question from Arthur. How long does a pyroclastic flow stay hot for?
Oh, good question. So it really depends on how the temperatures that the volcano is erupting with itself, and how long the volcano is erupting for. So, for example, the one in Pompeii, that pyroclastic flow lasted for 24 hours because the volcano was erupting for 24 hours. So the ash that was, or the pyroclastic flow, was just followed by more pyroclastic flow and more pyroclastic flow, building up the ash on this city time and time again. In terms of distance, it can go on for sort of several kilometers as this avalanche down the side of the mountain. So basically a really long distance.
Great, thank you, Jack. And Stuart asks, what is the best material, if there is one, to stop lava in flow?
Ooh,
Can anything stop lava?
Question. Good question. I guess obsidian it's quite a strong material that's made from basically cooled lava, and it is what sort of coats the inside of the main vent of a volcano. So that's, although some of the chunks from the main vent may break off as the magma is rising, it tends to do a good job of keeping the volcano structure and stopping the lava, although eventually if you expose it to enough, it will break down as well. In terms of something you can build your house out of, not really. The best case would just making it really, really thick, to give yourself a bit of time to withstand the volcano.
So essentially we just need to stay out of the path of lava, don't we, basically?
Yes, yeah, that would be my advice.
Yeah. Fiona and Arthur ask, do you know what the biggest eruption has ever been?
Yeah, good question. So the biggest eruption that's ever been, it's difficult to say because we don't have the complete records, obviously, in sort of dinosaur times. We don't have no one was there to observe their own dinosaurs were, but they weren't writing anything down to pass on to us. One of the biggest that we, in sort of recent years that we know of, was in 1815, and I'll get the name of this right. It was Mount Tambora in Indonesia. It erupted, and the explosion, it was an explosive eruption, and the explosion of the initial eruption was heard 1,200 miles away from the volcano. So that's just a good idea of how explosive it must have been for just the sound to travel that far.
God, that's amazing. And Thomas asks, would lava melt diamonds?
Oh, would lava melt diamonds? I would assume eventually. So diamonds are very, very strong. Diamonds are made up of carbon that's been compressed over millions and millions of years in the Earth's surface. I would assume that they would be able to, because it's a compound that makes up the Earth's crust, and the Earth's crust itself, everything in the Earth's crust, can be broken down by the mantle that's below it and turned into magma. So I would assume yes, although diamonds are very, very strong, we use them in drills to drill through the Earth because of that reason. But I think lava, if you give it enough time, will still be able to melt the diamond.
Great, thank you. And what happens when lava meets water, which kind of links with, this is one question we got, and Heidi says, can water stop lava in its tracks?
Yeah, good question. So we actually have, not every volcano is on the surface of the Earth. Well, not every volcano is on the land surface of the Earth. We can sometimes have underwater volcanoes or underwater volcanic vents. And what happens at those, that's a really good example of lava meeting a lot of water, meeting an ocean. And when what's happening is the lava just gets cooled by the water, and it gives off a lot of steam. So in areas where we have these underwater volcanoes, we often won't see the lava, we'll just see the rock pouring out of the vent and instantly being cooled and giving off a lot of steam. So above the surface of the water, you'd see quite a lot of bubbles, quite a lot of steam, hot steam coming off of it. That's what's happening. The water will cool it, but you need a lot of water, like an ocean's full of water.
Brilliant, fantastic. And last question I think we've got is, are there any other sort of famous big cities that have been destroyed by volcanic eruptions, like Pompeii?
So Pompeii is definitely the most famous. I'd go, yeah, so especially in Indonesia. So Indonesia's just sort of sits between Australia and Asia, and it's in the Ring of Fire. The Ring of Fire is a area of the world that sort of spans up the west coast of North America, South America, right round the top and down the east coast of Asia and Oceania, so like New Zealand and places like that. Around there, there's a high volume of volcanoes, and there's been many times where those volcanoes have erupted and destroyed towns and cities as well.
Great, fantastic. And one last question that's come in from Fiona and Arthur again is, what temperature is lava when it's kind of flowing down towards you?
Yeah, good question. Lava itself won't always be as hot as the pyroclastic flow, but it will be reaching those temperatures. So it'll be reaching temperatures of about 1,000 degrees Celsius, which is very, very hot. As we know, it would tend to be more in sort of if we were talking about a non-explosive where the lava is just pouring down, it would probably tend to be more towards 600, 700 degrees Celsius in those examples there. So that's a more common temperature, but it can reach hotter temperatures. It can be cooler temperatures as well.
Great, fantastic. Thank you, Jack. That's all the questions we've had in, so I shall hand back to you for the next stage.
So to explode our volcanoes, of course, we're going to need a volcano to start off with. But before I do that, what I'm going to do is I'm going to lay down on my sort of eruption surface. I've just got a plastic bin bag. Now that's just to sort of stop it from going on my carpet, things like that. But if you've got a big table that you're putting it in the middle of the table, that should act as fine. But you might want to put some sort of protection underneath so that you're not going to get fake lava everywhere. Basically, and try and contain it as much as you can. So that's what I've got here, and I'm going to put my volcano on top of that. The first thing we want to add to a volcano is our vinegar. Now, vinegar itself, depending on which type of vinegar you've got, if you've got white vinegar, it's white. If you've got sort of other types of vinegar, it can be brown. You might want to make it red. So what I've done before I started is I've taken some vinegar and I've poured it into this bottle here so we can see it quite well. And I've added a bit of paint. Now, if you've got red food dye, anything like that, anything that could turn it red, you just need to mix that into your vinegar at this stage. And what that will do is when the eruption is happening, it will just make it look a bit more like lava instead of bubbles. You'll still get a cool effect, but just the red color makes it look a bit more dangerous, a bit more like lava. And I've also poured it into something, sort of a container that's going to make it easy to pour into my volcano itself. So that could be a jug, it could be a bottle with quite a small neck. I was originally going to use a glass, but what I found with the glass is that by pouring it, it kind of misses quite a bit and you don't get as much of the vinegar in. So once you've done this and once you've got your vinegar, you want to pour in enough so that it fills your bottle about a third / half of the way. And obviously you can't see the bottle in that. So again, it's another reason why I've used a similar sized bottle to the one that I know is in here, so that I can see that I'm using about a third full of vinegar. So once you've got that, you want to carefully pour it into your volcano, trying not to miss as much as you can. And hopefully, there we go. So hopefully in there now, I've started to fill up the magma chamber of my volcano. Starting to get the magma chamber is full. When we add the baking soda, what we'd expect to see is the magma chamber to get even more full and sort of start the magma start to rise up the vent and pour over as lava. So the next stage we need is the baking soda stage. So I'm going to take the spoon I used earlier, and I'm going to also, for this stage, use a folded piece of paper. Here it is. to act as like a funnel to help me pour in the baking soda into the top of the volcano. Because as soon as I pour it in, like you saw with the glass, the reaction happens quite quickly. So you want to be able to pour it in and stand back so you're not getting covered in your fake lava. So the way I've sort of made this is I folded a small square of paper in half and then in half again, and open it out a little bit, and it's creating sort of a V shape that I can put a teaspoon, maybe a teaspoon and a half if you've got a larger bottle of baking soda in. So I'll do that now. Again, there we go. We've got to put in a heaped teaspoon, which is just about a teaspoon and a half full. And I'm going to fold it up and hold it in this V-like shape. A little bit's leaking out, but that doesn't matter too much. But what you can see is when I go to pour it in the top of my volcano, what we should hopefully is that it all pours in quite quickly, and then I can step back and watch the eruption. So I'll do that now. And if you've got yours ready to go at home, you can do it at the same time. I'll tilt the camera down, so those of you who can see this can see it quite clearly. And hopefully when I pour this in, we should get some sort of an eruption. So if I start just pouring that in, I can hear it starting to fizz up. If we don't get an eruption, I might add a bit more. There we go, we can see it coming out the top and starting to erupt. It's sort of explosive, this one. You can see it exploding out the top there. Perfect. So that's the eruption. You saw the lava. I'm going to, in fact, see if I can get it to erupt a little bit more by pouring slightly more vinegar in the top as well. So if I use an empty glass. Yeah, so the good thing about this is not only do you get the first eruption, but once you've got that, you've still got vinegar in there. You've still got baking soda in there. So if you just add a little bit more, we can sometimes get a second eruption. So that's a little bit more vinegar. See if I can put a little bit more baking soda in there as well. Take that down. Just make sure there, maybe a little bit more vinegar as well. But yeah, sometimes you can get a second eruption as well by just adding a little bit more. So that was sort of my volcanic eruption. I'd love to see what your results are at home. So once you've sort of done this, and make sure you video it as well so you can watch it back and see your eruption. The good thing is, again, once you've erupted it, all you need to do is sort of wipe it with a cloth, pour out whatever's inside. If you've got spare vinegar after and spare baking soda after, you can erupt it a second time. Again, so yeah, make sure you sort of enjoy this and video it so you can watch back. And if you do make a video, be sure to send it to us on email or on Twitter so we can see it too, because we love seeing what you've made. If you've got any other questions or anything about how your volcano is going at the moment as you're erupting it, feel free to type them in the chat as well, and we can answer those. But that's all from me. Thank you very much for joining me today.
Great, thank you very much, Jack. We have actually had another question come in while you've been doing your eruption, which is from Stuart. What is hotter, out of pyroclastic flow or napalm?
Ooh, I don't know a lot about napalm, but I imagine pyroclastic flow. Pyroclastic flow is incredibly hot. It's very, very difficult for us to create temperatures hotter than pyroclastic flow on Earth in a lab, for example. So I would imagine that it would be pyroclastic flow.
Marvellous. Excellent. Thank you. And thank you very much for the lesson in general, Jack. It's been very helpful. And I hope people at home have had a chance to either erupt their volcanoes or learn everything they need to know so they can do it later on.